So in this video, I'm going to continue our study of inverse functions by talking about inverse trigonometric functions. I'm not going to go into everything that I need to with inverse trigonometric functions in this video. There will be one follow-up video to this one. Specifically for this video, I want you to know the domain and range of inverse trigonometric functions, and I also want you to understand the geometry behind trigonometric and inverse trigonometric functions. This will definitely come in handy a lot as we continue to do more and more calculus. So the first thing I wanted to mention to you is what the Pythagorean theorem says. I know everyone automatically jumps to the last part, but the first part says that if the triangle is a right triangle, as in it only works for right triangles, then a squared plus b squared equals c squared. There's actually different relationships if it's not a right triangle. Now, the next thing I want to talk about is, again, trying to define these trigonometric functions based off of geometry. So all of these functions are going to take in an angle. And in this case, the angle that I'm going to use, or the symbol that I'm going to use to represent this angle, is actually theta. And one of the things we're going to talk about later is we're specifically using radians as opposed to degrees, although the angle itself is just the angle. Now, sine is going to use the opposite over the hypotenuse. So based off of this angle, the opposite side is A, and the hypotenuse is always this side across from the right angle. So it's going to be A over C. Cosine uses the adjacent and the hypotenuse. So this side that this angle actually happens to be sitting on, that's not the hypotenuse, is the adjacent side. So B over C. Tangent uses opposite over adjacent, so that'll be A over B. Cosecant is the reciprocal of sine, so I'm just going to flip it over and do C over A. It is hypotenuse over opposite. Secant is hypotenuse over adjacent. It's the reciprocal of cosine, so it's going to be C over B. And cotangent is the reciprocal of tangent. It's adjacent over opposite, so it's B over A. Now, when I mentioned before about inverse functions, what they do is they take in the output from the regular trig functions and they spit out the input of their original trig functions. So what I want to happen for a triangle, specifically a triangle, I want it to take in the side ratio of A over C, and I want it to spit out theta. The same thing happens with cosine. I want it to take in B over C and spit out theta. I want it to spit out that angle. For tangent, I want it to take in A over B and spit out theta, the angle. So again, remember A and C. A is the opposite over hypotenuse. For sine, let me repeat, sine is opposite over hypotenuse. For cosine, it's adjacent over hypotenuse. And for tangent, it's opposite over adjacent. I'll write down for tangent, opposite over adjacent. Cosine is the other one. It's adjacent over hypotenuse. Now, same kind of idea for cosecant inverse. What it's going to do is it's going to take in those sides, C and A, spit out in the angle. Secant inverse is going to take in C over B and spit out the angle. Cotangent inverse is going to take in B over A, spit out the angle. Now, I will also mention to you while I'm writing these down is sometimes we don't write sine inverse like this because it can be a little confusing. So we'll write arc sine. They're going to mean the same thing. Same thing with cosine inverse. I might write it as arc cosine. They do mean the same thing. And with tan inverse, I'll sometimes write arctan. Again, they're meaning the same thing. It's just to try to prevent confusion with that -1 in the exponent. Remember, this is not actually an exponent in this case. It's referring to an inverse. I just wanted to make sure I made that clear. Pythagorean identities. So there are trig identities that are important related to the Pythagorean identity. If you want me to go into where these actually come from, I'll be happy to do that in a different video. But I'll list all three of them down real quick. So the first one is sine squared theta plus cosine squared theta equals 1. The next one is going to be tangent squared theta plus 1 equals secant squared theta. And the last one is going to be 1 plus cotangent squared theta equals cosecant squared theta. These are nice relationships that kind of, again, relate back to the Pythagorean theorem, but also relate to our trig functions and how I can change from one trig function to another without being too difficult. Some of the other identities that are important are reciprocal identities. I already mentioned 1 over sine is actually cosecant x. The same thing as 1 over cosecant, it just switches back to sine of x. Cosine's reciprocal is secant. If you do 1 over secant, you get back to cosine. If you do 1 over tangent, you get cotangent, and if you do 1 over cotangent, you get tangent. The other identities that I think are important are the ratio identities, is that sine over cosine is actually tangent of x, and cosine over sine is actually cotangent of x. Now, the last thing I want to talk about, and this is probably the most important thing that I want to talk about in this video, is the domain and range of the trig functions and their inverse functions. And so what I actually did was I went ahead and graphed these using computer software to try to make my life a little easier as I try to go through and explain these. For example, the first one I did was y equals sine of x. And I want to point out that right now this is not a one-to-one function, because if I tried to draw a horizontal line, it fails. It touches it repeatedly over and over and over again. So what I need to do is I need to make it one-to-one in order for it to have an inverse. And the way that we do that is we restrict the domain. I'm going to make it so that I cover every value from top to bottom, quite literally top to bottom, and not have any repeats in there. And the way I'm going to do that is I'm going to cut it off right here at its bottom, at its minimum, and right here at its maximum, at its top. Notice that if I zoom in on those x values, that's negative pi over 2 and positive pi over 2. So that's how I'm actually going to restrict the domain of sine to make it one-to-one. It's going to be from negative pi over 2 to positive pi over 2. The range, if you notice, the lowest point it goes to is a y value of -1, and the highest is +1, so its range is -1 to 1. Now, for the inverse functions, they just switch. So the domain, it's going to take in a number from -1 to 1, and it's going to spit out a number between negative pi over 2 and positive pi over 2. And this is going to be important because I'm going to mention it more in the next video about kind of what happens here when I have some interesting cases. It's going to be a little bit different for cosine because, again, cosine is not exactly the same, but it's pretty similar to sine. Notice in this situation, it starts out at its top. It starts out at its peak, and then it goes down to its trough. It goes down to the bottom. So notice in this case, I'm going to use my x value as 0 for my starting place. And I'm going to end at, I don't know, I kind of marked it out there. Let me erase that. It ends at pi. So that's going to be my domain for that one is 0 to pi. Its range is, again, the y values. Its peak is at 1. Its trough, its minimum is at -1. So we'll go from -1 to 1. Notice, again, we always put the lower number first, bigger number second. And when we do inverses, we switch it. So it's going to go from -1 to 1 and from 0 to pi. So I'm going to take a number from -1 to 1 for cosine and plug it in, or excuse me, cosine inverse, and plug that in, and my answer will be between 0 and pi. For tangent, tangent looks completely different. It has this nice, I'm going to call it a cubic shape, where it starts off way down here on the bottom, travels all the way up, passes through 0, 0, and keeps on going. Now, this one's going to be a little bit different because if you notice, it kind of looks like it actually has vertical asymptotes, and, well, the answer is because it does. So there's vertical asymptotes here at pi over 2 and at negative pi over 2. And these vertical asymptotes will tell me, A, it's undefined at those two places, and any other vertical asymptote, notice there's more here at 3 pi over 2 and more here at -3 pi over 2. So tangent is undefined in a couple of spots, but it also actually makes it easier because I can just cut off the domain at those places. And instead of putting brackets where it is equal, I'm going to put parentheses because it's not defined at those two places, negative pi over 2 and pi over 2. And its range, notice it keeps on going all the way down and keeps on going all the way up. So its range is -infinity to positive infinity. So if I plug in a number between negative pi over 2 and positive pi over 2 into tangent, I should get any number, like literally any number, for the output for its range. So when I do inverse, they switch. I can plug in any number I want into inverse tangent, and it will always give me an answer between negative pi over 2 and positive pi over 2, not including those two numbers. Now that I got those three handled, I'm going to go ahead and mention the others. So cotangent is going to be very similar to tangent. It just goes the other direction. So notice it starts at the top and it comes all the way down on the other side. It still has these vertical asymptotes. They're just no longer in the same place. They moved over a little bit. So notice the first horizontal, or excuse me, vertical asymptote, my apologies, is at 0. The other one is at pi, so that's going to tell me my domain, 0 to pi. Again, parentheses, not brackets. And its range goes from negative infinity to positive infinity. It goes all the way down to the very bottom and keeps going all the way up to the very top. For cotangent's inverse, again, just switch it, negative infinity to positive infinity, and 0 to pi. So I can take any number I want, plug it into inverse cotangent, and it will always spit out a number between 0 and pi. For secant, it's a little bit different for the range because notice there's no numbers here. Its actually highest point on the bottom stuff is at -1, and its lowest point on the top stuff is at 1. So it actually keeps going up to positive infinity from 1 and keeps going down to negative infinity from -1. So that's going to be an interesting range to write, and I'll show you how I'm going to write that in a minute. The other important thing to remember again is I need to make this 1-to-1, but notice it's a little bit funky in how I need to write this because again, there's still another vertical asymptote here, in this case, pi over 2. And the other thing I need to worry about is the fact that, again, it's not 1-to-1 at the moment, so I need to cut it up in a way that it is. So I'm going to cut it off here at 0, and I'm going to cut it off here at pi. So notice what that does is it covers this whole side, and I'll kind of darken it in a little bit. It covers this whole side here where it's going from 1 to infinity, and it also covers this whole side where it goes from -1 to negative infinity, but it doesn't repeat. So let me write this very carefully. My domain is going to be from bracket 0 to pi over 2 where there's an asymptote, and I'm going to put a parentheses. Then I'm going to put a union symbol and do pi over 2 to pi with a bracket, because again, it does reach pi. There is a number right there. Its range, and again, I was going to be very careful when I wrote this, its range is going to go from negative infinity to -1 with a bracket, a union from 1 to infinity with a parenthesis there. So notice brackets on -1 and +1, parentheses around negative infinity and positive infinity. It's actually kind of backwards because, if I look at the domain, it's a bracket and then a parenthesis, and then a bracket, whereas it's parenthesis, bracket, bracket, parenthesis. Uh, for inverses, they switch. So the domain will be from negative infinity to -1 with a bracket, union 1 to infinity. For the range, it'll be 0 to pi over 2, parentheses, union pi over 2 to pi with a bracket. The last one and the only one I still need to talk about is secant. Um, with secant, again, we still have a vertical asymptote. In this case, there's one here at 0. We have others here at like negative pi. We have another one at pi. But again, I still have to be careful to make sure that I make this 1-to-1. So one of the things I'm going to do is I'm going to cut it off here at negative pi over 2 and at positive pi over 2. What that does is if I look at the negative pi over 2 side, it starts me off at -1 and goes to negative infinity. If I look at the positive side from 0 to pi over 2, it starts me off at 1 and goes to positive infinity. So it covers everything I need it to. So in this situation, domain, we're going to say bracket negative pi over 2, parentheses 0, because again, vertical asymptote at 0, union 0 to positive pi over 2. My range, again, is going to be similar to secant. It goes from negative infinity to -1 with a bracket because it includes -1, union +1 to infinity. For the inverses, they just switch. Negative infinity to -1 with a bracket, +1 to positive infinity with a parentheses. Well, that is not a very good parentheses. Let's try that. And the range will be from negative pi over 2 to 0, parenthesis, and 0, parenthesis, to pi over 2, bracket. Hopefully this helps you guys better understand at least where these things come from, and the domain and range and how my input in one direction might change versus the output or the input in the other direction. That is something I always have had questions on. People have asked me many times is, especially when you're talking about sine and cosine, they're like, hey, I'm trying to plug in sine inverse of 2. Well, there's a problem with that. Sine inverse can only take in numbers between -1 and +1. You're never going to get an answer. It's not a calculator problem, it's a you problem. So make sure you're paying attention to just kind of that tidbit of information. The other thing that I think is really cool about this, and I did want to mention to you, is how sine and tangent and cosecant all are related to each other. Like they all very have that negative pi over 2, pi over 2. Let me again show you. There's sine, negative pi over 2, pi over 2. There's tangent, negative pi over 2, pi over 2. And there's cosecant, which is negative pi over 2 on one end and pi over 2 on the other end. The other ones that go together are cosine. Then you've got cotangent over here and secant. Those go together. They all have a very strong relationship with each other in how they are represented in their domains and ranges. Hopefully this does help you better understand trig functions and inverse trig functions and how they are related, and as well as some geometry and identities. Have a great day. Bye.